Hello and welcome to the Fossil Huntress podcast. Today on the show, we're going to be talking about fossil fuels and the Earth's mass. So I generally talk about fossils in terms of paleontology and long dead creatures that we unearthed from the Jurassic or the Cretaceous. But today we're going to be talking about fossil fuels. We've had a question from a bright young mind, and the question is, does the Earth's mass decrease when we burn fossil fuels? And if it does, is it measurable? And do we know how much of the Earth's mass has been lost so far? So, well, Melaina, the Earth's mass does decrease when fossil fuels are burnt, but probably not in the sense you are imagining, and only to a very, very small degree. So there is no decrease in chemical mass. When we burn fossil fuels, we rearrange the atoms into different molecules, and in that process, we release energy from those chemical bonds. But in the end, the same particles, protons, neutrons, electrons, remain, so there's no decrease in mass there. But energy is released, and some of that energy is radiated out into space, escaping from Earth entirely. Einstein's theory of relativity tells us that energy does have a mass, so that's that E equals mc squared you see rolling around. And when a chemical bond that stored energy is formed, the resulting molecule has a very tiny bit more mass than the sum of the masses of the atoms from which it was formed. So it's a net gain. So when you take two things and make three, you get something a little bit more than three. Again, this is an exceedingly tiny bit in very rough numbers. I put the chemical formula for this on the blog, but I won't read it to you because it will come out as gobbledygook. But it's a very exceedingly small fraction, so 50 billionths of 1% of the fossil fuels consumed each year. And of course, the energy in fossil fuels originally came from the sun. So in absorbing sunlight, the Earth's mass increases slightly. So I picture the Earth expanding and contracting, taking a deep breath, then exhaling. So we don't see the Earth expanding and contracting when we look, taking a deep breath and exhaling, but it's a great visual for the never-ending give and take process. I'm not sure how we'd measure the small changes to the Earth's net mass on any given day. The mass of the Earth is determined using Newton's law of gravitation. So it's given as the force, which is equal to the gravitational constant multiplied by the mass of the planet and the mass of the object divided by the square of the radius of the planet. So again, gobbledygook. But Newton's insights on the inverse square property of gravitational force was from an intuition he had about the motion of the Earth and the moon. We've seen that mathematical formula played out in many places. And I know Newton's law could use some curb appeal, but it's super useful when understanding what keeps the Earth and other planets in our solar system in orbit around the sun and why the moon orbits the Earth. So we have Newton to thank for his formulas on the gravitational potential of water when we build hydroelectricity dams. Newton's ideas work in most, but not all scenarios. So when things get very, very small or cosmic, gravity gets weird, and we head back to Einstein to make sense of it all. If you want to look up some very cool papers on this topic, there was one published in September of 2020 by Qing-Yan Fong et al. In the Journal of Nature that looked at heat transferring in a previously unknown way. So heat transferred across a vacuum by photons, so tiny atomic vibrations. And the effect joins conduction, convection, and radiation as ways for heating to occur, but only across tiny distances. So the heat is transferring by photons, the energy-carrying particles of acoustic waves, taking advantage of the Casimir effect, in which quantum fluctuations in the space between two objects that are really, really close together result in physical effects that we couldn't have predicted with classical physics. So again, when things get very small or very large, the universe gets weird and the rules bend. But the question was specifically about the mass of the Earth and the burning of fossil fuels, and that process does decrease the mass. So it is mostly true that the Earth's mass does not decrease due to fossil fuel burning because the numbers are so low, but it's not entirely true. The fuel combines with oxygen from the atmosphere to produce carbon dioxide, water vapor, soot, and ash. And the carbon dioxide and water vapor go back into the atmosphere along with some of that soot and ash. And the rest of what is left is a solid residue. So the weight of the carbon dioxide plus the water vapor and soot is exactly the same as the weight of the original fossil fuel plus the weight of the oxygen consumed. In general, the products of any chemical reaction whatsoever weigh the same as the reaction or reactants, but there's only one known mechanism by which the Earth's mass decreases to any significant degree, and that's molecules of gas in the upper atmosphere, primarily hydrogen and helium, because they're the lightest. They escape from the Earth's gravity at a steady rate due to thermal energy. This is counterbalanced by a steady rain of meteors hitting the Earth from outer space. So if you ever want to hunt them, fly a helicopter over the frozen Arctic. They really stand out. And they contain mostly rock, water, and nickel iron. These two processes are happening over time and all the time at a steady rate, unchanged by anything that we do. So the net is about the same. So the answer is that the Earth's mass is variable, subject to both gain and loss due to infalling material, micrometeors and cosmic dust, and the loss of hydrogen and helium gas, respectively. But the end result is a net loss of material, about many tons per year. And the burning of fossil fuels has an impact on that equation, albeit a small one. But it was an excellent question, and I appreciate you sending them in. So I pushed this episode forward because I'm sure this is something you need to know for school. I will post about this and put a couple of links so that you can check some references if you'd like to for your paper, and I'll talk to you soon. Thanks for listening.